Welcome to a quick physics video looking at the physics of forces. We are going to start off by looking at what a force does. Quite often you will come across forces called pushes and pulls, but that's a little bit of a simplification of what they're really doing. Ultimately, what a force does is cause change. We quite often group these into four effects of a force. So, for example, in the first one here, we can think of the force coming from the engine of a car acting through its wheels onto the road as changing its speed. We can also think of a force from a tennis racket applied to a tennis ball that may well change its speed, but will also, importantly, change its direction. On top of that, we can also, as in the kneading bread situation in the bottom left there, change an object's shape. And finally, like with wind turbines, when the force of the wind pushing on the blades causes them to change their rotation. Crucially, and here's a thorny idea, you've got to be careful with this thing, if something is already moving, if it's moving, say a spaceship out in space or a boat on a lake, it doesn't need a force to keep moving. Just as much as something sitting still doesn't need a force to keep sitting still. Forces cause change. Okay, we also need to know some specific forces. There's a bunch of different specific forces. We are going to talk about a subset here of the really important common ones. Okay, if I have an apple floating in the middle of the air, it won't stay floating for very long because it feels a downwards force. Now, there's loads of different names people can give that force. I'm going to steer clear of the word gravity here. It's a force due to gravity, but the force itself on a planet, and specifically on the Earth, because that's where apples are from, I'm going to call the weight of the apple. Different from its mass, dependent on its mass, and in fact we have a little equation just to link in with some other physics. We can think of that as being mass times the strength of gravity on the planet at the place you are. So we're just going to call that G is what that's called. Okay, second example on here. I've got Superman flying through the air. Because he's moving through the air and he has that wonderful flapping cape, he will experience a really important force called air resistance. Similarly, if he tried to fly through water, he would feel something called water resistance, and this is a specific type of drag force that something moving through a fluid like air or water or honey or oil will feel. And when it's air, we'll call it air resistance. That is probably the most common one you'll come across. The other type of important drag force that you will come across here is if something is moving on top of something else, or if you rub your hands together, you will feel friction. This is a drag force just like air resistance because it's going to go against motion. So if something's moving, it's going to try and stop it. But this one relies on physical contact between two things. Slightly more complicated examples here. If I have a pulling force along something like a rope in a tug of war, then I'm going to call that force tension. You may have come across this in the phrase a tension headache, which is a headache that feels like your head is being pulled on. So tension just means pulling. We have two specifically non-contact forces here. One is between charges and it comes from static electricity. This is called an electrostatic force. And similarly, if we have magnets, they can either attract or repel, just like with charges. These are just simply, we're going to call them magnetic forces. Two forces commonly confused here. If I have a plane, it doesn't fall down to the ground. When it's flying through the air, it is kept aloft by a force called lift, which is caused by the air moving over the wings of the plane and pulling it upwards. A boat doesn't sink because of another upwards force, but that upwards force, we don't really call that lift. This is, it has two names. I'm going to call it first buoyancy, but you can also call it upthrust. Those are a selection of the forces that you need to know the names of. There are others as well. But crucially, with all these forces, what we really need to be able to do is talk about what happens if I have more than one force, because we never really have only one force. But we still need to be able to work out what the total effect is going to be out of our four different options. To find out that effect, we're going to calculate something called the resultant force. Now, resultant force is just a fancy way of saying what's the total force that's acting. And the second thorny idea that we're going to come across today is that the direction of that force that we're thinking about here matters. We can't just add all the forces together, because if I have two forces acting in opposite directions, like here on my car, you can tell it's a car because it says car. I've got 300 newtons to the left, 200 newtons to the right. So what's the total effect? What's going to happen to my car? Well, if this was a tug of war, which essentially it's the same thing as, the left-hand force is going to win. This 300 newtons is bigger than the 200 newtons. And because these two forces are acting in opposite directions, I'm just going to subtract this 200 newtons from my 300 newtons, and that is going to leave me with a total force of 100 newtons. But again, the direction is important. It's acting in the direction of the winner, which is to say, to the left. That is our resultant force on the car. What will this cause the car to do? Well, it could cause it to do any of the four effects that we have above. Usually, what we'll think of this as doing is it will cause the car to change speed. Or it could be that the car is driving along and this force is acting to the left, so it's going to make the car change direction towards the left. I have a different example here. If I have a box with 10 newtons applied to it going leftwards and 15 newtons applied going leftward, what's the total force? What's the resultant force in this situation here? Well, these two forces are not opposed to each other. They're not acting in opposite directions. They're acting in the same direction. And in this situation, we simply add them together. So in total, I've got 10 and 15 going to the left. So in total, left wins, definitely, and it has a value of 25 newtons. Okay. Last example. This is a bit of a special situation here, and it's a really important one. If I have a boat on the open sea, and it's just sitting there, it's got an upthrust or a buoyancy of 200 newtons acting upwards, and it will also have a weight pulling it down towards the depths underneath it. If a boat is floating, those two forces will be the same. And if they're the same, well, neither one of them wins. And so, in fact, the resultant force here is 0. There is no total force, even though we're applying 400 newtons onto the boat. The effect of it is nothing changes. Bear in mind, if the boat was already moving, it would keep moving exactly the same as it would have before. But because here I've drawn it not moving, it's going to stay perfectly still. All right, hopefully that has brought a few of these ideas into a bit more clarity. Just to recap the really important things, a force causes change. It can either change the speed, direction, shape, or rotation of an object. If something's moving already, it doesn't need a force to keep moving, but if I apply a force to something, it will speed up. We need to know some specific force names. We've got weight, air resistance, friction, tension, electrostatic forces, magnetic forces, lift, buoyancy or upthrust, and many more. We also need to be able to add forces together to find the resultant force, but crucially, the direction of the individual forces matters, and so if they're acting in opposite directions, I subtract them. If they're adding in the same direction, I add them together, and sometimes we can end up with a resultant force of 0. Fantastic, thanks for watching.